Okay, so we can start. Please come on time, colleagues. We lost 10 minutes until we waited for you. So then, because we have a lot to cover. So we looked at data-driven modeling, the main sort of principles. I would like to ask you, what types of data do you remember that we use in data-driven modeling? Types of data. Class data, yes. Numerical, yes. And ordinal also we mentioned, which often is used as if it's class data, no problem, but also ordinal. But also there are other types of data, but this is a main types. Now, what we considered here is the algorithm for building a classifier. So classifier is a data-driven model that is able to classify newly coming input vectors into one of the classes, which we accept for this particular problem. So in this case, again, we have classes 0 and 1, and we want to classify newly coming vectors into one of the classes. And data for training this model we have on the screen. And if you remember, we were building three splitting space into blocks, and every time trying to keep in one block only examples belonging to the same class. That was an idea, basic idea of building this tree. Now we can say it's an overfitting model because it's absolutely accurate. We could, for example, stop here. Oops. Not doing this. It will be giving a small error here. We could have stopped also here. It would be robust model, not a small error here because we would think this is 0 class, but there are 2 examples of 1 class. So then, but then we would not overfit data. We would not be absolutely accurate in training. You remember that? That we shouldn't try to be absolutely accurate on training. But we also could build this model, and then it would look like a tree, like this. You remember? And we were able to classify newly coming vectors into one of the classes. Yeah? Now, what we unfortunately don't have time to go too much into detail into classifiers. However, in machine learning, this is the main actually interest of people to build classifier more than regression models, interestingly enough, because there are many classification problems that they want to solve. For example, face recognition is a classification problem. If you walk through the airport, your face is photographed, and then this face is compared to a large database, and they try to classify, does it belong to a class of people that you don't want, or what? Or on the fish sorting factory, there would be a camera that would photograph different fish, and fish which would not be processed automatically would be sent to one place, and the fish that's processed automatically would be sent to another place. So there would be binary classifier saying good fish, bad fish, something like this, okay? So here we're classifying examples into classes 0 and 1, or yes, no, whatever. But how do we draw these lines? So what was the reason to draw the first red line here? Think about this. Why I draw this line here? Maybe you draw it somewhere else. Also possible, by the way. Would be almost as good as this one. And this is not maybe optimal. I just used my imagination to draw this line. But I could use a formula. And then if I use a formula, then we could incorporate this into this model. And I can show you how to build automatic classifiers. Okay, I'll give a hint. And I think I already told you. So this line is drawn like this. It's a hyperplane. In multidimensional space, it's a hyperplane that would separate examples into 2 blocks. So I try to have examples belonging to the same class as much as possible in both blocks. That's an idea. So here majority is zeros, and here majority are ones. Not majority, maybe not, but okay, that's first split. Second split does the same. Look, second split also tries to separate examples belonging to one class into one block, examples belonging to another class into another block. Okay? So this is an idea. Idea. Where is this thing? And there was also a USB thing. Is it on it? Ah, it's hidden here. All right. Yes, thank you. Good. Yes, thank you. So then we'll be looking a bit more professional than moving hands around. Thanks a lot. Yes, thank you. So again, this line would split into blocks, trying to keep same amount, not same, but as much as possible, examples belong to one class in one block. So I will, you could follow this presentation. There is an example taken from Mitchell's book, and this example is used widely in machine learning community. It's called playing tennis example. So here we observe the person going to play tennis. There were 4 attributes that would take into account: outlook for the weather, sunny, overcast, or rainy; temperature, hot, mild; humidity, high, normal; wind, weak, strong; and output was to play or not to play tennis. I prefer to spend more time on neural network exercise than on this example, so please look at it yourself. And but I would like to show you the formula that is used. Where is it? Yeah. So how do we split the set of examples at every step? We split it in such a way that we would have majority of examples belonging to one class in one block. For this, we will use formula for entropy. So entropy says for a set S, if a set S has examples belonging to 2 classes only, entropy is calculated as probability to find by random picking example belonging to the plus or 1 class multiplied by its logarithm minus probability to find example belonging to class minus multiplied by its probability. It's Shannon proposed formula in the 40s when he wrote a book about information theory. If you want to know more about entropy, do your reading. So it's not trivial notion. But I would present you a very trivialized notion of this entropy, because we don't need to go deep into information theory. We just need, in this case, a formula that would give you calculated criterion to split the data set. Look, entropy here, if we put probability to find example of class belonging to plus class, like 1 or 0, plus, minus, the same thing, this formula would look like this. Sorry, this plot of S entropy against the probability. So if probability to find class plus is 50%, then entropy is maximum. So because the number of examples belonging to these 2 classes is equal. So we cannot distinguish much. But if probability to find class plus is approaching 1, entropy drops to 0. Okay? So if all classes, all examples belong to class plus, entropy is 0 here. So maximum entropy in a set is when you cannot distinguish these examples. 50% of class 1 and 50% of class 0. So we would be splitting this set in such a way that we'll be trying to have entropy in each set approaching what? 0. To have low entropy. It means to have examples belonging to the same class as much as possible. That's what it is. If entropy is maximum at 1, then we cannot judge 50% this, 50% that. What kind of classifier? It doesn't know what to do. That's an idea. So then, when we were splitting this set into, when I was choosing how to draw this first red line, algorithm, which is called ID3, formulated by Quinlan in the 80s, but there were also other authors which proposed similar algorithms. Okay, anyway, but this most popular, ID3, it's called Interactive Decondomizer 3, ID3, and then there were several versions afterwards. Anyway, the idea is this. I try to draw this line at all, I do exhaustive search. I try to draw this line first for x1 at each possible split. So I take first split along this example to separate this example, which is rightmost, this example. And I calculate entropy. I write it down. Then I move to the next possible split. I calculate entropy. I write it down. So for x1, if you have n examples, I have n minus 1 possible splits. So I have to calculate entropy n minus 1 times just for x1 split. Then I do the same for x2 split. I try to find. And every time I do n minus 1 splits for each of the dimensions. So if you have, okay, let's say n splits, if n is number of examples, if m is dimension of the problem, so I have m by n. So quite many splits I have to try. It's exhaustive search of the best possible split. And every time I write the entropy for these two sets. And when I find, when I find that entropy in these two sets is small, I choose that split for the further deliberation. So what I do, I calculate entropy in each subset, and I weigh it by the size of the subset, because it's important to to have big subset. So that's what it is. So this is a number of elements in a subset V here, and this total number of elements in set S, which I'm splitting, and this is entropy in subset V. So if I have binary class, I want to split only in 2, so this would be summation of 2, no problem, and this is total entropy at the previous set. So if entropy is small, this is large, so gain, information gain for me would be maximum because this entropy is small. That's how this algorithm works. Very simple, actually, easy to implement. You just go through all possible splits and calculate entropies at each set. Simply have to do it many times, so it takes a bit of time, but okay, computers are fast, so that's no problem. So that's an algorithm which would allow you to build a classifier for binary problems. Same you can do when you have several classes. Similar thing, just entropy takes a bit different form, and you also can do it. Any questions? No. So this works for simple problems of classification and widely used method, simple and straightforward. Okay? Good. So I told you in the beginning that I will split some of the slides, but you are welcome to look at them later. Simply, this course takes many more hours than expected. So I'll show you one example that we use where we used classifiers. It was decision tree. There were also other classifiers, not very important. So the problem posed was this. We want to build a classifier to replicate pumping strategy for a regional water system. So this is Delftland now. Rhineland, we considered it was, Delft is here in the middle. This is The Hague. This is Rotterdam over here, Rotterdam Port. And this area is below sea level, at some places 4.6 meters below sea level. So if you take a bike from Delft to Hoek van Holland here, you would go to through places which is really low, 4.5 meters below sea level. So you can look at sea like this. Now, there is a lot of pumping going on from the groundwater pump. It's pumped to some storage reservoirs, and then from them up, and there are a number of large, very large pumping stations that pump water from this polder. It's called the polder, or many polders actually, polder area, into the sea or into the rivers which are connected to the sea. Okay, so these are large pumping stations. So what we did, we took the strategy for pumping which we observed. So this is water level in one of the polders, in one of the polders. This polder is called Woudse-Droogmakerij. Can you pronounce this? No? Then it's useless what I'm doing. We have to learn this. So you are given a couple of days to learn. Woudse-Droogmakerij. So, and this is Delft storage basin. So there are pumps that pump water from this polder into the storage basin, and then water is pumped further to the ocean. So the water level here is shown. You see water level 4.6 meters below sea level, so it's minus. You see this? So you see somewhere here, so it's minus. Anyway, we want to keep water level low, so when water level goes up, we switch on the pump, big pump. Water level goes up because of rainfall, or because maybe of some inflows, okay, but mainly it's rainfall. So when water goes up, you see we switch on the pump. Do we have zoom in? Yes. So this is zoom in. So look, water goes up, we switch on the pump here, we pump, and then pump is switched off when water level goes down. Then it's okay, here pump is switched on. Here when we see small increase, pump is switched on. Then we see water level goes up, pump is switched on, works, and switched off. So you see pump has 3 states, 0, 1, and 2. Because pump consists of 2 pumps actually, so 1 or 2 can be switched on. So that's what people were doing. So it is not optimal pumping, but okay, not bad. So that's what experts were doing. So we wanted to build a simple classifier that would give us the value of pump output, 0, 1, or 2. That's why it's classifier. 3 classes, based on the state of environment. In this case, just water level. So we were taking water level now and pump discharge at the previous time step, and output is pump discharge now, that we have to decide now to switch it on or off. If 0, it's off, 1 is on, and 2 is very much on. Okay? So why do I need pump discharge at previous time step? The thing is that this pumping station is a huge device, it's a big thing, and we don't want to switch on the pump every 15 minutes. We better run it for some time, like here. Maybe we could switch off here because this water level is not dangerous, but still we're running the pump to reduce water level. So it's not good to switch on the pump off every 15 minutes. It's not good from engineering purposes. That's why we think it's important to remember what was the pump switched on or off at the previous time step, and it would have influence on our decision now. So this is output from Veka software actually, and this is decision tree. So the model is written up here. F is this classifier. Input is water level now and pump at the previous time step. And pump T is pump now. It's class 0, 1, or 2. And this water level is real value. Okay? So this model allows combination of class values and real values. And then Veka build us the tree, so that's the tree which should be like this, okay? So first question is this, is pump T-1 0? Was pump switched off at the previous time step? If yes, then we check water level. Is water level now below minus 4.577? If yes, we keep pump at level 0. We don't switch it on. However, if water level is above this level, we have to check again water level against 4.57. You see, it's almost the same, but still we do it. And if it's below, it's still 0. However, if it's above, Then if it's below 4.5, then it's medium pump, and this is high pump. So it's one pump switched on and it's two pumps switched on. So it's a simple decision tree. We every time check different conditions of inputs, and then we make a decision, then we generate output. It's advice for decision maker. If he looks, my classifier says 0, maybe I should put 0 or 1 or 2, switch on the pump, or maybe switch it off. Okay, so what does this classifier, this model, model? What does this model model? It models previous experience with this pumping strategy. This pumping was done by experts. So experts were switching on pumps or switching them off, every time having some judgment about this. And we recorded all this data. There were thousands of different time steps, so actually more, but we took maybe a limited part. Sorry, thousands. You see 2,000 time steps we took. This is zoom into so that you can see. So we took that data about how pumping was done by humans, and we encapsulated that knowledge into this classifier, into this tree. Now, if an operator of this pump would decide to switch it on, it would be useful for him or her to look at what classifier actually gives you an advice. If classifier says switch off and you want to switch it on, it's a question, because this model encapsulates data of the experience of other operators. That's the use of this classifier. It's not automatic that classifier would switch on pumps. It gives advice to an operator how other operators in the past were behaving in a similar situation. Is it clear? Good. So now we tested it, of course, so this verification. So this is a fragment when 100% correct classification was done. You see, green and pink known pump status and predicted pump status are exactly the same in this fragment. However, if we looked at another fragment, it's not always the case. So you see that known pump status, for example, here was don't switch the pump, but predicted pump was saying green, switch on the pump. So here you have, you can say classifier error, yes, and this is the life. So always models make some mistakes. Okay? In this case, we use training set and test set. So this is on the test.
And what about these places that we have predicted pump on and off at the same time?
What? Give me the number. 610. Yes. Here, look. Here, classifier says 0, but operators in the past were saying pink. But look, there are more. So this is here misclassification, but next one is correct. Then again misclassification, then again correct. So these are not subsequent time steps. They're one by one, or there is something in between. Okay, so it's like this. Right? So that's what we did. We could talk about classifiers much more, but I would suggest to move to regression models, neural networks. And also one of the reasons is that neural networks, being regression models, can be used for classification, and very often used. And how, you will tell me how. After we discuss neural networks, I will ask you, and how can you use neural networks for classification? Right? Just to check if you understand what we're talking about. So we now assume, when we talk about regression, that output is, what type of data is output then? Numerical, yes. So real valued output, and inputs for neural networks are also, for regression models, are typically also numerical, but not always. They could be classes as well. But then you have to do something. You have to convert a class value into real value and only then use a regression model. Okay, so But we assume now everything is numerical. There are many different models. ARMA model, maybe you know, for time series, linear and nonlinear regression, of course, where we should always start with linear regression, and artificial neural networks, and also there are regression trees and model trees. Now, I prefer not to go into regression trees, model trees in detail. However, in our course at IHE, we do it in detail and we have exercise. I just want to tell you quickly what it is. So Bremen in 1984 suggested something called regression trees. It was not very good name because there is not real regression. So what he did is this. If you have dependency y on x, and this is data collected, this method assumes that let's build separate models for two blocks, for the left-hand side and right-hand side. And indeed, why not? Because here you have higher values of y for this block, and here lower values of y. So why don't we build local models? So this principle of building submodels is widely used because submodels would be more accurate because they represent what's happening for low x, and this is for high x. So why not? But Bremen said, let's use zero-order regression. Zero-order regression means that this coefficient A0 is 0. So in fact, it says y is equal to a constant, A0. It's called zero-order regression. This is first-order regression. First order because x is to the power 1. Okay? So Bremen strangely suggested to use zero-order regression. It's strange for me. Why not to use linear regression, which Quinlan did several years later, which would be a very natural thing, to split sets and build linear regression models here instead of zero-order regressions. However, okay, Bremen was followed by, because he was famous statistician, still is, I think, in Stanford University, and this idea was followed by many, and there is a software which commercial software can buy, and these regression trees are widely used. And Quinlan's model trees are used less. So what Quinlan suggested in '86 is to build linear models here. That's a natural idea, isn't it? You make a nonlinear model overall, nonlinear, but locally it's linear. So he developed algorithm which is called now M5, and it's implemented in Veka software, and you can use it. So it's quite successfully builds nonlinear model which are piecewise linear. So we can say it's a piecewise linear model. How to build these models here and how to split, maybe we need a lecture to discuss it, but it's based on this continuation of idea of entropy. But I will not go into detail here. So if you want to learn more about model trees, read a book from authors from New Zealand who developed Veka software, actually. And it's all in detail presented. So his paper is short, but Australia and New Zealand, they work together, I suppose, and they wrote very good books about this, and they promoting M5 model trees a lot. And we also use it in research. Okay, this is how we build model trees here. So in our split now, output is not class, but output is real valued. It looks at u, okay? Each point here is a vector of two values, x1, x2, and value of y points at u. This is the output. And in the end, we built similar tree model. It's M5 model tree, but in the model here is not a class, but there is a linear regression equation. In each model, there is a linear regression equation. So linear regression is built on the basis of this subset, which you find in this block. That's how model tree works. Okay. There are some examples. You can look at our papers where we used, for example, paper in Journal of Hydrological Sciences. For Hoeha River, we built a predictive model. Shall we run out of this room quickly? No? It's okay? Some strange noises. Anyway, so we built a model which would have so many different inputs. like drainfalls, and output would be predicted flow at the downstream. So, and model 3 would look like this with 7 models, but you can build many more models. Right, colleagues, with this, we're approached to start with the neural networks, and let's do it. So we looked at presentation which is called part 1, okay? So I close it now, and we go to the presentation which is called part 2. I think it's called part 285, or maybe 86. Yes? Do you have it? 86, good. Right, so neural networks. When people talk about artificial intelligence, very often they say neural networks, saying these are synonyms. Well, not really, but indeed neural networks is a very popular technology used in machine learning. And there are different types of neural networks. Currently, there is deep learning neural networks and very different neural networks, but we will look as an introduction only at one type, which is called multi-layered perceptron, which is actually the most widely used neural network. And it forms the basis for deep learning neural networks, actually. And there are different forms of it, different functions used, different combination of neurons, and so on and so on. They may have memory in it or not. So there are different types. So if you want to know more, consult book of Heiken, the best book on neural networks, I think. And there are also smaller books and maybe a bit faster introduction to them. I could recommend you these books. There are many books on neural networks. All of them are reasonably good. So let's start again from linear regression. And linear regression forms the basis for every neural network. And if I say a node, I would assume there is a neural network, sorry, there is a linear regression equation here, which is written up here. And we can train it again by solving this optimization problem, which is not written here, but I did it before, you remember, trying to minimize distance, vertical distance from each of the points to the model to be built, which is this green line. So linear regression builds a linear model, and neural network actually builds non-linear model. Well, it's just illustration, don't look at it seriously. So what we'll do now, we will build a linear regression model now using Excel. There are different ways of doing this, but I want to show you a very quick way of doing these things. So please open Excel. So I did it already here, but I would like you to replicate what you see on the screen and do it yourself so that you have some feeling. So Excel, laptop, and type in this table, please, of only 8 examples. So we have 8 examples. X is 1, 2, 3, and so on, 8. Okay, very simple. You can say it's time series. And output is 4, 5, 7, 9, 10, 11, 11, 9. Okay? So let me remove this and do it with you. So then we mark this like this. And I will do it in a very simple fashion. Yeah, please tell me when you are done. Done with the numbers? Okay, so we say insert, and we insert recommended charts, and please insert this chart, which is scatter with straight lines and markers. So this is obviously non-linear relationship. Okay, so let's try to build our first data-driven model. And in Excel, there is a nice feature which says trend line. It's not really linear regression. You can also go to data and build linear regression, but we'll not do it now. We'll use Veka for this. So if you right-click on this, one of the points, there would be Add Trend Line option. Add Trend Line. Okay, and what you see here is this is linear regression model. There is no equation here. If you want equation, you go to another option, but okay, here it's good enough. So it's a linear regression model. Accurate? Well, not really. So here it's okay because there's not much nonlinearity, but here obviously it goes down, but linear regression points to infinity. So disadvantage of linear models that with the increase of x, they would infinitely increase y. And often it is not true. In most natural processes, this is not happening. Most natural processes have nonlinear character. So we could improve this model, and if we make it quadratic model, look, it becomes much better. So this model has two parameters. It's written as a0 plus a1x plus a2x squared. It's this model. And it builds a nice nonlinear model now. Okay? Okay, now you remember the blue line. So it was, you remember the green line, then there was a red line, this red line, and which is much better, but a bit more complex. Maybe we should stop here. But let's build a model which would have zero error. Well, we do it here quite simple, a nice feature. We increase the order. It means we add terms to this polynomial. It's a polynomial model. So it has the form a0 plus a1x plus a2x squared plus a3x cubed and so on. So if you increase the order, look what's happening. Model becomes more and more accurate. You see? And then it doesn't change much. But model goes through all points exactly. So perhaps its error is 0. Look, it goes through all points. Well, maybe in this case it's a nice model, but you remember we had a very strange thing when it was not a good model. So I could reproduce this if I move this point some here. It would have very strange. Can I move this point actually? So this is 9, right? So if we make it 4, okay. Yeah, above order 6, so it's behaving strangely. It tries to be accurate here, but here it cannot pick up all the points. Okay, doesn't work like this. Anyway, so that's a demonstration how we can use Excel to build simple models. Okay, you can close this. What was here initially? 9? Yeah. Right. Neural network is this. It's a multi-layer perceptron network. The first ideas started to appear in the 40s when community of artificial intelligence, it was not called like this, but people coming from psychology and other areas started to think, or neurologists started to think, can we reproduce, let me show you immediately this. Idea was this, if already brain structure was known, that brain consists of neurons. These are neurons, and there are billions of them, and they're somehow connected. So this connection are electrical and chemical. So these neurons send to each other electrical and chemical signals. So, and it works like this. When the neuron sums up effects of different impulses coming to it, then there is a sort of stepwise function, and if summation of these impulses exceeds this threshold, then neuron fires. So it sends impulse to another neuron. That's how it works. Very simplified picture, of course. It's much more complex in reality. But scientists thought, why don't we, if human brain is so clever, it can do so many things, why don't we, using computers that has just appeared imitate this working of the brain, and maybe we create artificial intelligence. That was an idea in the 40s and 50s. So they started to develop this idea and came up with an idea that since we have neurons, so these are these neurons here, and this as well, and you may have many layers of neurons, so this is two-layer network, which is widely used, but you may have many more layers in this neural, then it will be called deep learning, okay, nowadays. And if these are inputs, these neurons would process this information, and if we have this nonlinear function in these neurons, then when we have signals here, it would be this, and when we have signals, it would be this. So it brings in nonlinearity. Also, these functions sometimes are stepwise. You can also do that, but then it wouldn't work as well as this one. So there was a switch to these functions. And they studied in the 50s and 60s different types of neural networks, and then someone wrote a book that neural network cannot solve nonlinear problem, XOR problem actually, and research was stopped for 10 years because National Science Foundation was not giving grants for something that doesn't work. It was really a pity, so that's interesting when one book, opinion of one person actually, and several maybe around him, influenced research globally. But then Verbos in 1974 proposed a method to train this network and to find coefficients, parameters in this network. And then everything started to develop again. So let's look at the detail of this neural network. So what are these? So this is also called input layer, but there is nothing happening here. We simply distribute inputs, values of inputs across several neurons here. These neurons and this are similar. They look like this. It's a linear regression equation here. You see this? Linear summation of inputs. So look, this is input 1 multiplied by A1 plus input 2 multiplied by A2 and so on. So they're coming here. So input 1, X1 multiplied by A1. Then input 2 multiplied by A2 and so on and so on. So this is summation. It's purely a linear regression thing. But if they all would be linear, it would be overall linear regression model, because you multiply, put the terms for each x1, and you would have linear model for x1. But they introduce the neural network uses nonlinear terms. So this f here then transforms linear combination of inputs into output, which is a nonlinear function. So for low values of this output of this linear regression model, you have almost 0, and for high outputs you have almost 1, and in the middle, actually here you have linear, so it's almost linear regression model, but here you have some nonlinearity. So these two pieces of function is enough to make this device universal function approximator. That's amazing how small pieces of plot make it universal function approximator, which is used around in engineering and whatever you take. If we take a computer, there are neural networks here which would, when you have internet, they would automatically train internal neural network to remove the noise on the lines and so on. If you see a tram going, there would be a control system which uses neural network to optimally control the voltage given to motors and so on and so on. So in your mobile phone, there are many neural networks that adjust behavior, train behavior based on your, train the functioning of the phone based on your behavior. So, nonlinearity. So let's take this neuron. Then this neuron fires output. So it calculates this output here, F. And then in this node, you have the same thing. You have again linear combination of inputs, but these inputs now come not from this input, but from output of these neurons. So it's distributed, you see, to all the neurons like this. And then again, the same function used, nonlinear function. So you have combination of many multiple neurons, which are internally quite simple, actually. It's quite simple function here. But there are many of them. So being combined, they present very complex function, and they're able to approximate practically any function of multiple inputs, you see? And note there are multiple outputs here. So there are many functions that you can approximate. Often, however, we use neural network with only one output, like discharge. If we calculate discharge, it's only one output, and we will use only one output, but nothing prevents you to have multiple outputs here. Any questions? No. So you know now what neural network is. Okay, I have a question to you. How to find these weights? You see these coefficients here, A and B. This is what people couldn't understand for 15 years after this was proposed. They didn't know. And I think they simply didn't read the books on nonlinear optimization. That's my explanation. Otherwise, I cannot explain it. They started to invent this backpropagation, whatever. I mean, of course, it's nice words, and indeed, it's backpropagation, but there was no need for that. If you would write down the formula for the error of this neural network, you would see it's a nonlinear function, differentiable, so we can use gradient search to find these weights. And there was no problem in the mid-80s to write down this algorithm because all of them were already developed by then, or most of them were developed. Mid-60s, sorry. In mid-60s already it could have. So you see, a bit of ignorance of some scientists against other disciplines leads to delay in research globally. So that's an interesting story. So how do we find these weights? So this is the error function. We use mean squared error. Okay, it's not mean because we don't divide by number of inputs here, but fine. Number of examples. Anyway, we use typically squared error. So, and training neural network is finding such values of weights, these coefficients, that would bring error to a minimum. Same as in linear regression model, if you remember. Same thing. So let me now, okay. These neurons, let me now go into details of this neuron. This hidden node on neuron, it's the same. It's this one, hidden. So inside there is an input going in, linear regression and nonlinear function. So you write it down like this. Here instead of f is g, sorry, but it's the same function. And output node is very similar, but inputs come from hidden nodes here. And linear regression again, and linear function, a nonlinear function, which is the same g here. And this is what it is. So we already looked at it. Logistic function we discussed. This is the formula for logistic function, and it's like this. And note here it's almost linear in this part. We should have had a break 15 minutes ago. Okay. So give me 1 minute, so we'll stop then in 1 hour. Okay, one property of logistic function is very nice, and perhaps that's why it was chosen to be used widely. It appears that if we want to find derivative of this function, it can be expressed through the function itself. So when we would be calculating gradients, you would need gradient derivative, partial derivative of, well, not partial because there's only one u. So derivative of this function. But you can write it like this. Because exponent being found derivative is exponent. So that's why it's so easy. So it's very nice here. You see the derivative is calculated by function. So in terms of, it was thought about when computers were slow. So people were nervous about calculating gradients and derivatives. So you can see that you simply calculate g once, and then you have only one multiplication plus maybe this, but alpha is often 1. Then you have only one subtraction, multiplication. Extremely fast operator to calculate derivative of g, which is very nice. This is a copy from the book of Smith, actually, where it is shown how these simple functions, sigmoid functions, being combined in a neural network could replicate complex function like this. one sigmoid functions looks like this, another one like this like this like this, but when they're combined, summed up, they make this. So you see very complex nonlinear function being sort of a mountain or Gaussian function like this is replicated by a neural network quite accurately actually, using very simple functions. So you see, idea of using simple functions and then aggregating them is very powerful. And actually, the great scientist, mathematician Kolmogorov in 1957, before neural networks, he didn't know about neural networks. In 1957, he wrote a paper where he proved that you can approximate any function to any given accuracy using multiplication and summation of simple functions. And this is what's happening here. Neural network is multiplication and summation of simple functions, and it's able to approximate anything. But Kolmogorov proved it theoretically before neural networks were invented. But these people haven't read his paper, I think, in time. It was later discovered and linked. Interesting. Okay, then we'll look at an example. After the break, time for coffee? You agree? What does neural network tells you?